because they're both very short units, and they're also probably relatively fresh because we've still been using integration techniques even when we're doing continuous random variables. So, having gone over it with the other class, they're much more excited about integration than they were calculus, because I think the general consensus is it's a fair bit easier. So we'll do both Chapter 4 and Chapter 5 as a summary today. So I've got a summary of the rules for Chapter 4 here. We've got basically the rules for integration. Maybe if I can just talk quickly to that unit, right? So this unit, remember I told you guys I wasn't heat happy with the order that the textbook presents it in. And even then there's a couple of sort of useless exercises that just get you to start thinking about anti-differentiation. So in 4a, we'll do a question like this today. We've got area under the curve using rectangles. In 4b, they're introducing you to the idea of anti-differentiation. So really not something we need to test. Properties of definite integrals, we've got integration from derivation. So that's the link between when you differentiate something and when you integrate something, the link between those two. We've got rules for integration, integrating f of ax plus b, and we've got definite integrals. So let's get straight into it then. So here's our first question. We've got the integral of 6x squared plus 5x take 7 with regards to x. And so when it's asking this, it's saying, what did you differentiate to get this? All right, that's what we're trying to solve. What did we differentiate to get this? And so we know the integral of x to the n is x to the n plus 1 on top of n plus 1. So I'm going to integrate it without simplifying. N plus 1 on n plus 1, plus here we'll have 5x squared on 2, we'll have take 7x, and then we'll have plus c. Got a couple of exams. You see the first page, there's maybe some calculus, maybe some integration, but it says differentiate or integrate without simplifying. Don't forget your plus c's. Excellent, so that's the first one. Let's go to the second one. We have e to the 4x plus 3 with regards to x. So when we're integrating e to the ax plus b, it's going to be 1 on top of a, e to the ax plus b, and then plus c. Alright, 5x take 4 to the power of 3, so this is ax plus b to the power of n. Okay, so just using the rules, we're going to have 1 on top of a, that's the coefficient of x, and then we have ax plus b to the power of n plus 1, on top of n plus 1, and then plus c. Okay, so this is what we're asked to perform, but we can't integrate that yet because we need to express it at the top of the fraction as a power of n. So this will be alright, and now we're ready to evaluate it. Again, it's ax plus b to the power of n. This 8 is just going to hang out the front, it's not going to move. So we're going to have 1 on 7. Ax plus b to the power of, sorry, that should be negative, shouldn't it? Because we've brought it to the top. Right, so it was at the bottom as a third, and when we bring it to the top, it becomes negative. So we have minus a third plus 1 on top of minus a third plus 1. And then chuck the plus c out the side there. Okay, and all that can be simplified and so forth, but we've performed the main integration here. Okay. We have a definite integral, and in chapter 4 we weren't specifically told the significance of a definite integral. We were just sort of evaluating it. It's in chapter 5 when we look at what does it mean. So, definite because it has these boundaries, right? We look over at these questions over here, we're not given a boundary, and that's why we need the plus C. Here we have a boundary, so when we integrate, we don't need to consider C. So integral of cos, I'm going to rewrite this first, just so you guys can see. Remember, whenever we have something written like that, if we can, we should consider it like this. And the reason that's helpful is because it's cos of AX. It's cos of some number multiplied by X. Sometimes the division can trip people up. All division is multiplication, right? Okay, so now we're ready to integrate. We have cos of AX. It goes to 1 on A sine of AX. And we're going from 0 to pi on 2. Now 1 divided by a half simplifies to 2. Now we're ready to sub in pi on 2 and half. That's going to be sine of pi on 4. On to question 3 then, we have using two rectangles, find an upper estimate for the area under the curve y equals x squared over the interval 0 to 2. Okay, so this is exercise 4a. We have the function y equals x squared, and we're doing it from x is 0 to x is 2. All right, we're going to use two upper rectangles. So that means each rectangle is going to have a width of 1, right? So here's the first upper rectangle. Here's the second upper rectangle. And if the function is y equals x squared, then the y value here is 1. 1 squared is 1. And the y value here, 2 squared, is 4. So therefore the area of the upper, the first rectangle is 1 times 1. And the second rectangle is 1 times 4. This gives you 5 units squared for the upper estimate. Alright, part B. Calculate the exact area using technology. So the exact area is the integral from 0 to 2 of the function x squared. X is 3 on 3, 8 on 3. And because it's an area, unit squared. There's two ways we can do that, right? We can graph the function x squared and g-solve the integral in the graph, or we can just write this statement in runner, right? Put that in runner and evaluate it and get the 8 on 3. Okay, so that's using our calculator. Part C, will the lower estimate or the upper estimate be closer to the actual area? Right, here's we've done the upper estimate. We haven't calculated the lower estimate. That would be one way of answering it. Okay, we could say, we could calculate both and work out the difference. But let's talk about it. Here, this function, and some of you did this in the folio task, x squared is concave up, which means it's opening upwards. So what we're going to do then is let's look at the error associated with each estimate. Okay? So if it's concave up, that means it curves like this. I'm going to exaggerate it for the purposes of demonstrating my point. It's concave up, it demonstrates like this. And if we do the upper estimate, they're above the curve. And if we do the lower estimate, that's below the curve. And so here we have error of upper. Here we have the error of lower. And we can see this has a larger area of error. There's more coloured in there, all right? And so when it's concave up, the lower estimate is going to be closer. All right, it's closer because there's less error involved in the estimate. Okay, so that's that question there. So that's pretty well chapter 4, right? We did some rules for integration, and then we did a little bit of the rectangles and so forth. Very good. So let's flick over and let's look at chapter 5. Again, was a short unit. We have the applications of integration. So we did area under the curve using integration. We did area between two functions. We did some kinematics, and then we did some problem solving. So we've got here all 4 of those. So let's jump into 5b. We've got find the area between the function x squared and y equals 9. So the first thing we're going to have to do is sketch it, right? Here's x squared, and then the line y equals 9. Doesn't matter the x value, the y value is always equal to 9. Alright, so we have y equals x squared, and we have y equals 9. So we want to find the area, right? It's always going to be the top function, take the bottom function. We want the area of this shaded region. That's bound by 9 and bound by y equals x squared. But we also need to know what's the boundary over which to integrate. Where do they meet? Okay, so those functions are going to meet when x squared equals 9. So if we write that, x squared is 9, square root both sides, we'll get x is plus or minus 3. So here we have x is minus 3, here we have x is positive 3. And so the area between these two functions is going to be the integral from minus 3 to positive 3. Of the top function, 9, take the bottom function, x squared, with regards to x. Okay? And then it's just a matter of processing that. Now, one way we can simplify this a little bit, and you may see this pop up in solutions occasionally, so I want to make it clear to you. We can clearly see, right, that this function is symmetric about the x-axis, about the y-axis there. Okay, so you have each side the same. So one way you could simplify the calculation, right, is to make it the integral from 0 to 3, but 2 lots of it. Okay, do you see that? We're just gonna do this area, but we're gonna multiply it by 2 to get the whole thing. The reason that's simpler is because when you come to substituting in the bottom boundary, you're just putting in 0, and so it just goes to 0. All right, so I'll evaluate this one for you. So we're going to have 9x, take x to the 3 on 3, from 0 to 3. Look at that, nice. Just goes to 0. Right, you're not subbing in minus 3 and processing it and so forth. So we'll get, what do we got? 27, take 9, 18, 2 times 18, 36. Area, so answer in units squared. Okay, so it's only going to work if it's symmetrical, but it can be a way to simplify a calculation like that. Kinematics. We have a particle has a velocity function, v of t equals 1 take 2t, as it moves in a straight line. Find the total distance travelled in the first second of motion. Alright, so the first thing we need to do is sketch the sign diagram here to figure out if it changes direction. Alright, so if this is velocity, it's going to change direction if there's a change in sign. So let's sketch the sign diagram. So we're going to go, alright, equals 0, solve for t. We've got t is half, so there's a root at half. And it has negative slope, which means it's going down like this. So it goes from above to below. So initially, it was moving to the right, and then after half a second, it starts moving to the left. Okay, positive velocity moving right, negative velocity moving left. Okay, so we've got the sign diagram. And like I'm gonna do both. I'm gonna draw the graph here for you guys as well. Alright, so here's what the graph is going to look like. That's its root, and it has a y-intercept of course of 1. When time is 0, the y value is 1. When time is 1, the y value is minus 1. Alright, so it's a velocity time graph. T, V of t. And so what that tells you, we can see positive velocity, so it's moved to the right over there, and then it's moved to the left here. Let's answer the question. It says, how far has it moved in total? What's the total distance that it travels? So So we need to know what's the area of this component, and then add it to the area of this component. And you can make a geometric argument, that's absolutely fine. You can make an integral argument, that would be fine as well. I'm just going to go geometric, I think it's simpler. So the area under the curve, we'll just call it A, is going to be, we've got two triangles, and they're actually the same, aren't they? We've got the same dimensions, so we've got two triangles, and the area of the triangle is half the base times the height. Alright, and so if we consider the first triangle here, it's going to be half the base times the height. Okay, and then we'll just process that. 2 times a half is 1, so we're left with a half. So the total area under the curve is a half, which means the total distance the object has traveled is half a, what's our unit? Centimetre. So we can answer that in a sentence. The object moves the total of half a centimetre. Now, this calculation here, this is what it asks us to do next. It asks us to do the integral from 0 to 1 of the v of t function. Integral from 0 to 1 of the v of t function. Why would that not be the total distance? Well, if I evaluate that, what's it going to come up with? 0. Absolutely, it's going to come up with 0. And why is that? It's because this is evaluating this as a positive and this is a negative, and they're going to cancel each other. What does this one mean? What's the significance of it? That's the displacement, okay? It moved a quarter centimetre to the right, a quarter centimetre to the left, so it hasn't changed its original position despite travelling half a centimetre in between. So yeah, displacement, to answer that part, find the displacement of the particle after 1 second. The displacement is 0. Alright, so a bit like in calculus, we're considering the sign diagram. Velocity function, area under a curve, can help you generate total distance and the total displacement. Alright, problem solving. We've got the rate of traffic flow past a pedestrian crossing between 8 and 8:30 is given by this equation. I'm going to write it up. Provide a sketch. Okay, the graph is shown alongside. Find the rate of traffic flow at 8:20 a.m. So it hasn't said estimate it, so we should find it exactly. So what we can do, you can see it pretty clearly here anyway. When time is 20, the traffic flow here is also 20. Alright, so here we've got time, and here we've got the rate at which cars are coming through. So let's answer it. R of 20 is equal to 20, and what's our unit? Cars per minute. Okay, there are 20 cars coming through. And then when time is 20, the rate is 20. Use the graph to estimate when was the rate of traffic flow at its greatest. So it's going to be greatest when R of t is maximised here. So we can go that straight from the graph and you get what? T is 5. So when t is 5, let's answer in the context of the question. That's going to be 8:05 a.m. Alright, shade the region corresponding to the integral from 10 to 15 of R of t. So that's from here to here. We're just going to shade it. Explain what this region represents. So if you calculate that area, we have a rate function. Area under a rate is always a quantity. So that's going to be quantity of cars that pass through. The intersection. Between 8:10 and 8:15 a.m. Okay, part D, how many cars passed between 8 and 8:30? So you're going to do the integral from 0 to 30. Alright, so on the x-axis we have time in minutes past 8 a.m. Of the R of t function. Alright, and if you evaluate that, I think you get 1,031, 1,041. Cars. So in integration, if it's an integration question, you're always going to be presented with some rate. Alright? And in integration, we move from a rate to a quantity. Okay, we move from a rate to a quantity. Alright, in calculus we do the opposite. We start with some quantity and then we move to a rate. Alright, so we're going to spend the whole lesson doing that, pointing out the difference between calculus and integration. For now, let's direct our efforts to integration. So I encourage you, review sets, revision guide. If you haven't looked at that, please have a look at that. Otherwise, let me know what else I can give you to support you over the next 55 minutes.